Hey class, welcome today again. We are finishing up chapter 3. So we're in section 3, chapter 3. You're on page 40, roughly in your notes. So go ahead and turn to slide 40. Teacher, go ahead and pause this video while they do the bell ringer. Okay, the answers for the bell ringer. You should have said a mole is just simply an amount of substance. That's your 4 words. Avogadro's number should have been 6.022 times 10 to the 23. And molar mass, your answer should have been the mass of 1 mole of an element, or the mass of 1 mole. So today we're going to finish up talking about our slides. And so before we start looking at this slide, let me just kind of bring up a concept. Do you know where the concept of a foot came up when we talk about distance? Why do we call a foot a foot? Why do we say there's 5,280 feet in a mile? I've always heard rumors and stories, I don't know if it's true, that they used to use your foot to take a measurement of the size of whatever you were buying. So if you wanted a piece of wood, they would use your own foot, step it off, and they give you that length. And I've also heard rumors that it was the king's foot. The king's foot decided what the measurement was for the whole kingdom. Whatever it was, wherever it came from, understand that when we make measurements like a feet, all it is to show us the comparison. A foot is not really a foot or not really 12 inches. The only reason it exists is because we as people say it exists and we accepted it. It's only there to show the relative distance or relative whatever measurement we're doing. It helps me explain why my car is 20 feet long. It helps me understand why my shoe might only be 1 foot long. It just, again, is there as a way for us as humans to show relatively the comparison of these measurements. So think about that in terms of mass. Why is a pound a pound? Why is a gram a gram? It is only there because someone said at one time a standard of what a measurement was. Well, I don't like measurements. I want to create my own measurement of standard. And so what I want to do is I believe that I am the perfect human specimen there is. Now, again, I'm joking, but I weigh 200 pounds. So we're not going to operate off the concept of 200 pounds anymore, but we're going to say that everything in this world is going to be measured based upon Lawrences. So if I weigh 200 pounds, I am 1 Lawrence. Let's say if you as a student weighed 100 pounds, we're not going to say you weigh 100 pounds anymore, but we're going to say you weigh half a Lawrence. Let's say there's something out there that weighs 400 pounds. We're not going to call that 400 pounds anymore, but we're going to call that 2 Lawrences. And so because I rule the world, because I said what this measurement was, we're going to operate off the unit of a Lawrence, which happens to equal 200 pounds, and everything else is going to be measured in either a Lawrence, a half a Lawrence, or 2 Lawrences, or 3/4 of Lawrence, whatever it is. So all we did is we just set a standard, and we compared everything else off of that. The same idea happens in chemistry. How do we have the mass of an atom? Because it's relative. What we did was we decided that carbon-12 was the perfect specimen of an atom. It has 6 protons and 6 neutrons, and it's just perfect. And so we said that this is going to be the standard that all other elements are expressed in their masses. And so mass of oxygen-16 would have a mass of 2.656 times 10 to the negative 23 grams, but that in comparison to carbon-12 helps us decide what its atomic mass is. So all we said in chemistry was carbon-12, you're perfect. We're going to use your mass as the standard. Just like if we went to a world where Lawrences was the measurement for mass, you would measure it in Lawrences. But since we look at carbon-12 and we're looking at its mass, we already knew that carbon roughly had 6 protons and 6 neutrons. And so because it has atomic mass of 12, and because carbon-12 is the isotope we're working with, we were able to say that 1 AMU, by definition, is exactly 1/12 the mass of a carbon-12 atom. So where does this term AMU come from? It exists because it's just a relative standard. We just happen to say, look, 1 AMU is 1/12 of carbon-12 because we think it's the perfect atom. Just like I think we shouldn't say 200 pounds anymore, we should say 1 Lawrence, and that's going to be the standard of measurement. So when you look at carbon-12 and you think about it, since there are 6 protons in carbon and 6 neutrons, we say that each AMU, 1 proton weighs 1 AMU, 1 neutron weighs 1 AMU. And that is by definition because that is 1/12 the mass of a carbon. Now, over the years, as we've gotten more and more refined in our measuring skills and in our equipment, we can see that that number actually comes out to 1.00726 AMU, and this comes out to 1.008765 AMU. Now, the reason for that mass difference is not really known yet. I got a couple of theories myself on that maybe I'll share with you someday. But for the purpose of this class, we're going to keep moving, and we're going to understand that these two are roughly right on the money to the same. And they are there because they're defined as 1/12 the mass of carbon. And then when we think about the electron, just remember, we've already said the electron is about 2,000 times smaller, or if you want to be specific, it's 1,836 times smaller than the mass of a proton. But where do these numbers come from? It's because we define carbon-12 as a standard, and we say you are the perfect measurement. So based upon that, we look at our periodic table, and everything on our periodic table is massed in AMU based off of its comparison to the carbon-12. So where did all these masses come from, these average masses on our atomic weight? Well, that unit, that AMU, all came because we said that one AMU happens to be 1/12 of carbon, and all the other numbers we use on periodic table are all used in reference to the mass of carbon-12. So think about it. Look at your periodic table and tell me what is the element that is 4 times the mass of carbon-12. You should have your periodic table out, and you look on here, and you would find titanium. Titanium is roughly 47.867 AMU, so that would be the mass of whatever it is. It's 4 times the mass of carbon-12. Now, what element is 1/3 the mass of carbon-12? You should look around, and you should find helium as 4.00. So we can begin to see here is that just because we set up the system of what an AMU is, all based upon the relativeness of mass compared to carbon-12, but we can begin to identify and recognize different elements by their mass. And what we do over the years is we found out that different elements have different masses, and the reason for that now is because of the protons and the neutrons. And so what we do is we consider what we have as a chunk of something. I have a chunk of carbon. Again, copper. This chunk of copper doesn't just have one atom of copper. It doesn't just have 2 atoms of copper. It has like billions upon billions of copper atoms in here. But not all copper atoms have the same atomic mass. Some of them have 29 protons and like 30 neutrons. Some have 29 protons and like 31 neutrons. Some have like 35 neutrons. Some have 36 neutrons. So because we have different isotopes, the same element with different masses, the average mass is going to be different. And so that's where we come up with the average atomic mass. And that is the number found on your periodic table. This number in the top left corner, that red number, is the mass of that element of all its isotopes that are found in nature. And so all it is, it's the weighted average of all the masses found in nature of that element. So for this class, you need to figure out how to do this yourself. How do you find the average weight? And so here we're going to do 3 problems. So Mr. Teacher, I will need you to pause to give the students a chance to work on this, then to show them the answer. But I'll show you how we do the first one. So here's an example. If I gave you 100 marbles and there are 2 different sizes, you would see that 25% have a mass of 2 grams and 75% have a mass of 3 grams. Well, how do I find that mass? If this was 50% and this was 50%, then yeah, it's easy to find my mass, and it would be 1.5 grams. Or if I just had 2 marbles, I had a marble of 2 grams and a marble of 3 grams, and I found the mass between the 2 marbles, it would be 1.5. But when I begin to talk about percentages and have more measurements there, I got to come up with an equation or a way to solve this problem. So here you can see, and it's on the board, line A, 1A, and 2A. These are the same way to answer the same question with 2 different methods. The way I prefer to do it is this. Set up your problem to where you have 25%. But instead of 25%, let's just normalize it to 1. Percent just means divide times by 100. So let's take away that percent, divide it by 100, and we're going to turn that into 0.25. Then we're going to multiply that by the mass of 2.00 grams. Then we're going to add that to the next percentage, normalized to 1, so 0.75, times that by the new mass of 3 grams, and it's going to give you 2.75 grams. Now, your book shows you to do it this way. I don't like doing it this way. It's a little more complicated, a little more chance for error in your math. But if you want to do it this way, you take 25% times 2 grams plus 75% times 3 grams, and then divide that whole number by 100. Do it however you feel comfortable, but I would recommend this way, just normalize it. So here's going to be a couple more examples I want you to do. Pause the video, teacher. Let them show their work on this. After the class tries it, you can show them the next slide. Line B has the answer for this problem. Now, teachers, show them this problem, and after a few minutes,